Welcome back, everybody. We are still in 2.1. I decided that I'm going to start going through these additional exercises as well to give you some explanation for some of these. These are, again, really good additional exercises for you to try on your own first, and then check the videos and the notes to review later on. So we've got a number of examples here, and I've got some partially worked out just to save a bit of time. So we'll start with number 1, which is, let's find f prime for the function f of x equals sine x. So we're going to find the derivative expression for sine x. And this is a very common style of proof for this. So if we did f of x equals cosine x, it's going to look very similar. And even tangent of x would look similar as well, possibly, but a little bit messier, of course. So we've got our limit definition written down here. So I'm using the definition with f of x plus h minus f of x over h. So that difference quotient where we're letting h shrink to 0 as opposed to x approaching a number. Because I want the general function expression, right? So I'm not looking for f prime of 2 or f prime of 1 where I might use that other definition. So let's go ahead and get started here. So the question for this one is probably, where do we start? And so the only thing we can really do with this expression, if we're looking at it, is expand the sum here, right? So this is where we're going to want to use what we referred to as the sine-wich last year. So sine of two numbers added together, the angle sum, is going to be the same as the product. Oops. Sine x cosine y plus cosine x sine y. And we typically write the sine on the outside, so that is the bread, top and bottom pieces of bread of our sine-wich. So I'm going to use this for our first step here. So we're going to get the, let's keep it all in black for the moment. So we have the limit as h goes to 0, so we're going to have sine x cosine h plus cosine h, cosine x sine h minus sine x all over h. All right, so we've done our expansion here. So we can look at this expression and then try to think about, all right, so next, what are the sorts of things we can notice? Well, the first thing we can notice is that there's two sine x terms. There's two terms that have sine x in it, so we could do a factorization where we factor that out. And other than that, I think we're kind of stuck because cosine h, sine h, those aren't very helpful with each other, and there's no other cosine x in the expression. So I think I'm going to reorganize this. Let's see how much space we have here. Yeah, let's go ahead and go over here. So I'm going to rewrite that as the limit as h goes to 0. So why don't I rearrange terms first, and then we'll do some factorization. All right, so I'm going to just swap the second and third term, and then I'm going to factor out that common sine x between them. So we will move our work over here. So factoring out the sine x, we're going to get sine x cosine h minus 1, again, plus cosine x sine h, still on the right here. Okay, and then this is going to be really nice because it's over h. And what we'll notice here is that we're approaching 0. I've got cos h minus 1 over h, which is that special trig limit for cosine, which will be 0. And I also have sine h over h. So our next step here would be to split the expressions. All right, so again, I'm going to split those expressions up. We can put brackets around it just to indicate that it's the entire expression. And then the last thing to notice, our limit depends on h. So sine x and cosine x, for all intents and purposes of our limit, are like constants. We can ignore them. They're not going to change as h changes. So that means we can just apply the limits directly. So we're going to get 0 times sine x plus cosine x times 1, which means the derivative of sine is cosine, which is a really, really nice, beautiful result. Because what that tells us is that when I graph my sine function, right, so here's my sine function. If we were to, kind of step by step look and say, okay, what is the slope, right? So here, the slope is definitely positive. So what's cosine of 0? Well, cosine of 0 is 1. Okay, so the slope of sine at 0 is 1. And then if we think of the cosine graph, the slope, just like the cosine function, decreases, right? So my slope becomes less steep and then flattens out. Oops. And it is 0 at the peak. And then it's going to be negative 1 here. So as I sketch here, that'll be the steepest value of my slope when it's negative 1, and 1 of course. And then it's just going to go back up, etc. So each one of these red points is the slope of my sine curve in black. All right. For number 2, this is more of an interpretation of the derivative, right? So below we are given the graph of f prime. So again, this graph is the function of the slope values. So f prime of 0 we can see is negative 4 down here. And then f prime of 2 is 0. Easy enough. It says if f prime of 1 is negative 3, what does this tell you about the graph of f? Right, so f has a slope of negative 3 at x equals 1. All right, so again, that's going to be our slope. And then now we have this fourth question, which is f of 4 minus f of 3, is it positive or negative? Right, so if we look at our two values here, so at 4 and at 3, so 3 to 4, is here. So we can clearly see that our graph is above the y-axis, which means the slope is positive. And if the slope is positive, that means on the interval 3, 4, f is increasing. Right? It's got positive slope, which means as we move left to right, the y values are getting bigger, which means f of 4 is bigger than f of 3, which means that it's positive, since f prime of x is positive on 3, 4. Okay. So that fourth one is really the important one, because that is kind of introducing the idea that if I have the graph of my derivative, I can make statements about the original function without actually knowing any information other than the slopes of that function. So note, I don't even know what f of 4 and f of 3 are, but it must be positive. All right, and then we've got some Oh, sorry, we have a fifth point here, sorry. Is it possible to determine the values of f from its derivative graph? And the answer to that is no, right? We don't have any values of f of x. So we would need at least one value. Right, so if I have one value of the function, I have all values of the function if I know the derivative. So the derivative can be used to find other values. For number 3, we're going to make some observations about symmetries. So an odd function. So we'll just note if we are at c and negative c. If we think about the slopes, they are equal. So f prime of negative c equals f prime of c. Right, so equal slopes if they are odd functions. And similarly, if we take an even function, let's take our quadratic here, at opposite values, they're going to be the opposites of each other, right? So they're going to be the exact same slope value plus or minus with a difference of plus or minus. So f prime of c is equal to the opposite of f prime of c, which sounds like it's in reverse, right? Because what this is saying is that the derivative of an odd function is an even function. And the derivative of an even function is an odd function. So if we have an even or odd function, the derivative will change it to the other type of symmetry, which is a very nice result, especially when we look at polynomial rules. All right, so last one, we're going to take a function, find the average rate of change versus the instantaneous rate of change. So again, more of a vocabulary problem. So average versus instantaneous. So the average rate of change is just the slope of the secant line that passes through those 2 points. So our typical calculation of slope, subtract the 2 y values divided by the 2 x values in correspondence with each other. So we should get, I think, negative 1/3 is what I ended up with. And then for the instantaneous rate of change, though, we need to know the actual derivative value. So we want to know at x equals 2. So the instantaneous rate of change at x equals 2. So I could use the function definition or the point definition. Now that I think about it, I want the instantaneous rate of change at 2. I'll stick with this one, but the other definition actually might be a little bit more simple to work out, but they're essentially the same. So we're going to rewrite our first difference quotient by finding a common denominator. So we'll have x minus x plus h all over x times x plus h all over h, which is going to nicely reduce. Oh, x's will cancel. So we get the limit as h goes to 0 of negative h over h times x plus h, again moving that fraction to the denominator of the numerator term, and then the h's will cancel, and what we'll end up with is negative 1 over x squared as h goes to 0. So we get negative 1 over x squared, so that means that f prime of 2 is equal to, negative 1 over 4. So that means the actual slope at 2 of the curve 1 over x is negative 1/4. But our average rate of change would be a relatively good approximation, right? So we took the average rate of change of plus or minus 1 unit from 2. So we went down 1 and up 1, and we got negative 1/3, which is relatively close to negative 1/4, not a bad estimation. And so note that's the key of these two ideas, is the estimate versus the actual, right? And we can make comparisons between them. All right, so that ends the additional exercises for 2.1. Again, I'll probably be doing these for the remaining sets of notes that we have for these new topics, just so you have an extra resource to use. So if you have questions, send me an email or come by the office hours. But otherwise, until next time.